Part 2 of derivatives and the shapes of curves. We left off in part 1 looking at the first derivative test, which basically says that if you have a sign change on your f prime of x, then you're going to have either a local maximum or a local minimum at the critical point where you're seeing the sign change. So that first derivative test is useful, and it may have to be used, but the second derivative test is actually a little bit more powerful. It can save you some time if it can be applied. And we'll see there's one case where it can't be applied. So second derivative test basically just says that the f double prime of x is continuous near c. So you don't have any breaks in that second derivative function near the c value. And if the f prime of c equals 0, so this is basically what we would use to find our critical points. So one of the ways we could find the critical points is if your first derivative is equal to 0. So if you do have a critical point there, and the f double prime of c is less than 0, so that means that it is concave down, so the cup is opening down, then the f of x has a local maximum at c. If it's concave down, that means you went up to the max and then down on the other side to get that concave down shape. So you got a local max there. And then similarly, if the f prime of c is equal to 0, so you have that critical point there, and the f double prime of c is greater than 0, so now it's concave up, so the cup is opening up, then the f of x is going to have a local minimum at c. So with this test, if you can apply it, you don't have to check for the sign change on the f prime. You just need to go to f double prime, and if it's less than 0, then you know that you're looking at a place where it changed from positive to negative relative to your f prime. And similarly, if the f double prime is greater than 0, then you know that your f prime changed from negative to positive at that c. So really useful. You don't have to worry about a sign chart if the second derivative test can be applied. So when might not it be able to be applied? Well, if the second derivative at the c is also equal to 0, the test is inconclusive. The first derivative test must be used instead. You'll have to go to a sign chart. So let's go ahead and look at an example of this and put all these things together. So we're going to find the local maximum minimum values of this function using both the first and second derivative tests. So I'm going to go ahead and go through the whole first derivative test so you can see that, but then we'll use the second derivative test again, and basically it'll just reinforce what we see at the end of the first, and hopefully you'll see that when it can be applied, it's a little easier than going through the sign chart. So I always recommend trying the second derivative test first, and then maybe you got to go back and actually put the first derivative test with the sign chart into play. But let's go ahead and see this. So the first thing we got to do is find those critical numbers. Still need those from the video that I did before this one. So we got to find those critical numbers. And we have the f prime of x. Using this f of x up here, we get 6x squared plus 6x minus 36. And that is a polynomial. The derivative is a polynomial. So the derivative exists everywhere. So we won't have any critical points, critical numbers at places where f prime does not exist. So we just focus on the f prime of x equaling 0 in order to get our critical numbers. And just set this equal to 0, and I'm going to go ahead and just factor a 6 out to get this x squared plus x minus 6. And then when we factor that, you get x plus 3, x minus 2. So 6 never equals 0, so we don't have to worry about that. From the x plus 3, we'll get that x equals negative 3 is a 0. And from x minus 2, we'll get x equals 2 is a 0 of that first derivative. So we got our two critical numbers here, and we can then go down and start looking at the first derivative test. So for the first derivative test, this is all about signs changing on either side of the critical number locations. So for the first derivative test, put that first in there, we need intervals of increase and decrease for the f prime. And we're going to use a sign chart to do this. So for the sign chart, I'm just going to put a little number line. I'm going to put the critical numbers on that number line and no particular spacing, just relatively spaced. So negative 3, 2, we'll put them in order from smallest to biggest, but that's about all I need to worry about. And then I'm going to put just some little fences here so I can clearly see there's 3 different regions I need to look at in terms of this f prime of x either being positive or negative. Is it greater than 0 or less than 0? And if it changes at negative 3 or 2, then that will indicate a local max or local min, depending on how the sign of f prime changes. So in order to do this with the sign chart, I am going to pick some test values. Negative 4 on the left of negative 3. Just pick 0 in between negative 3 and 2. And then I'll pick 3 on the other side of 2. And I'm going to plug this in to this factored equation. And the reason I do that is because it's real easy to tell if I'm increasing or decreasing based on is it a positive result or a negative result overall. And the 6 is always positive, so I'm not going to worry about that. Negative 4 plugged in x plus 3 will be a negative number. Negative 4 plugged in x minus 2 will also be a negative number. So I got a positive times a negative, which is going to be a positive result. So the f prime is positive there. When I plug in 0, 6, still positive. X plus 3 will be positive, x minus 2 will be negative. So a positive, positive, negative multiplied together, that'll give me a negative result. And for the 3, I'm going to get 6 is still positive, x plus 3 will be positive, x minus 2 will be positive, so positive times positive times positive. So f prime will be positive from that 2 on out to the positive infinity. And now what I look at here are places where the signs of the derivative changed. And they changed at negative 3. They went from positive to negative. So basically what that's saying is we were going up and then we're coming down. And if you go up and then come down, well, you reached a maximum at that place where you changed over. So the local max from the first derivative test would be at x equals negative 3. And then we go from down to up, or negative f prime to positive f prime at 2. So there's a local min at x equals 2. That's all you really need to do. So the sign chart, takes a little bit to do, but if you got to use the first derivative test, that's how you do it. So now the second derivative test, I'm going to kind of switch gears here. Technically, I've got the answer, but I want to show you that using the second derivative test, it can be easier. You don't have to do the sign chart unless you're trying to find the places where the concavity changed, the inflection point. So if you're just trying to find the max and min, second derivative test, I would say go ahead and use it. So for the second derivative, we need to find that. So f double prime, we're going to go back up here and take this result and find the derivative of that, which will give us the second derivative. That will be 12x plus 6. So f double prime of x equals 12x plus 6. And now for the second derivative test, in order to find the max and min, I know that I have my critical values already. You still have to find those. But I know that f prime of -3 was equal to 0. And the f double prime of -3 is going to be equal to -30. If you plug -3 into that expression, you get -30. That is less than 0. And by the second derivative test, you have a local max. Same result you got from the first derivative, just in what some people might consider a little faster approach, where you just get your critical points, then go to the second derivative, plug in the critical point, and if it's less than 0, you're concave down, which is indicating a local max. And similarly then for the second place here, the 2, got that equal to 0. And the f double prime of 2, you plug in the 2 up there, you're going to get a positive 30. That's greater than 0, so that you're going to have concave up at that point, which means you have a local minimum at that point. So same result, which should be the case from your first derivative, but notice I didn't have to use a sign chart or anything here to get the max and min. Some people like that a lot better. All right, so the last thing we'll look at here to finish off, where's the inflection point? Sometimes people will be interested in finding the inflection point or points. So where's the inflection points? How can we find those? Well, we still need to use a sign chart, and basically where f double prime of x is equal to 0 will be candidates for the inflection points. So we'll set 12x plus 6 equal to 0. And when you solve for x, you get x equals -1/2. And if you go ahead and make a little sign chart with the -1/2 in there, you got -1 to the left of that. Put a little fence here to separate the two regions. And I'll have 0 on the other side of that. And we're looking at f double prime now, where the f double prime changes sign. Is it going to go from positive to negative? Concave down, or I should say positive would be concave up to concave down, or vice versa, concave down to concave up. So plugging in that -1 into the second derivative, 12 times -1, -12 plus 6, still going to be negative here on the left side of -1/2. And if you plug in 0, you get a positive result. So it does change in sign from the left side of the -1/2 to the positive. Change in sign at -1/2 indicates inflection point at x equals -1/2. And that's all there is to it. So if you're looking for inflection points, even if you could use the second derivative test to get the max and min, you still got to use a sign chart to get the inflection points. Okay, if you have questions about that, don't be afraid to ask in the chat or if I see you. And otherwise, thanks for watching.